Hi everyone and welcome back. On the last video, we already talked about space-time curvature, but as the result of parallel transporting vectors along geodesics or along an enclosed loop. And we saw that the Riemann tensor was involved in this mathematical concept. So as a summary of last lecture, we saw that if we parallel transport a vector A alpha along an enclosed loop, it might come back not parallel to itself due to curvature, and the kind of curvature is determined by the kind of transformation that we observed when we come back at point P, and this vector difference is proportional to the Riemann curvature or Riemann tensor. And this can be written mathematically as this operator acting on the vector field P alpha. We said that it was equal to the Riemann tensor alpha beta, beta gamma delta contracted with a value. So the Riemann tensor at point P contracted with a value of the vector field at point P. All right, in this video, we will see how the Riemann tensor is involved in the geodesic deviation equation and how can we talk about space-time curvature in that way. So the concept is the following. If you start with two parallel geodesics and you introduce some very small difference vector here, xi or chi. Due to curvature, this geodesic might later on cross or diverge from each other or maybe remain parallel to each other. And so we are interested in this deviation vector, chi. We're interested in his sort of acceleration, his double derivative. So along the geodesics. So double covariant derivative in the u direction, and let me recall that u is this one, but it's also this one, but we start with both parallel, so it's the same. They are equal. And so we're interested in this double covariant derivative of psi. This is the geodesic deviation equation. That's how we can model gravity. That's how we actually can. That's a direct effect of gravity. That's how we see it. That's how we can quantify it, and that's how we can model it when we do some informatical simulations. So as a reminder too, I will just write here that the Riemann tensor, it's an invariant local measure of curvature. The Riemann tensor at point P describes the curvature in the fourth direction, time and the coordinate, the time coordinate, the x coordinate, the y coordinate, and the z coordinate. Everything is encoded in the Riemann tensor in terms of crystal symbols and so we're interested in this entity and we'll see that it involves the Riemann tensor at some point. And now that's the conceptual part is sort of done. And now we just have to dive into the math with some algebra and I'll try to skim it. So we know that for geodesics, this equals 0, and I can write it as u alpha u equal u beta equals 0. Okay, and now I'm interested in the covariant derivative of this in the chi direction. The covariant derivative of my vector u in the chi direction. So I want to see the rate of change of that that tangent unit vector of my geodesics in the chi direction as we move forward. So this, I write it as this. So in the chi direction of u alpha u beta, of course, it's still equal to 0. And this, I can write it as xi or chi gamma nabla gamma u alpha u beta equals 0. Okay, so I'm interested in this, which is not the geodesic deviation equation, but we see that if we develop this entity, we will somehow it will involve the Riemann tensor and the geodesic deviation equation, and we'll be happy. So if you develop this, I don't think I'm gonna do the algebra because that's not really the point. I mean, everyone can do it. Yeah, so basically we're interested in this, and if you work out some algebra, I will write it like this. If you do some algebraic steps, you will find the Einsteinian geodesic deviation, the geodesic deviation equation, the Einstein geodesic deviation equation, which we can write as which we can write like this. That's Einstein geodesic deviation equation. And that's the entity we were interested in. We were interested in this, the double covariant derivative of our deviation vector chi. and we find out that in the algebraic steps, it involves the Riemann tensor. And this is not so surprising. I mean, to go back to the conceptual part, uh, let me write that in general, if you have a positive spacetime curvature, so for example, a sphere, and you start at the equator with two parallel geodesic, you know that they will meet at the North Pole. They will cross each other and they will meet at the North Pole. And this is a sign of, if I denote the curvature kappa, this is a sign of positive curvature. For example, a cone, except the tip. On the tip, the curvature is positive, but everywhere else, the curvature is equal to 0. So if I start with two parallel geodesic, they will remain parallel. This is a sign of negative curvature. And did I say negative curvature? No, it's a sign of no curvature, sorry. And negative curvature, it's geodesic that will converge from each other. So for example, if I have a saddle point, or I mean, if I have a if I have a negative curvature, then geodesic they diverge, not converge. Did I say converge? I should really stop that recording, I guess. So the geodesics that diverge, negative curvature, converge, positive curvature, and if they remain parallel to each other, it's no curvature. And this we can see it because for each of these starting parallel geodesics, we have this chi deviation vector. And if we look at the double current derivative in the u direction, we obtain the Einstein geodesic deviation equation involving the Riemann tensor, which encode the curvature in all directions. And I think that's all. One can also compare yes, that's all I wanted to say for the Riemann tensor.